Welcome to my talk titled Python Meets the Crab. For those of you who are unaware, there's this programming language called Rust, whose mascot is actually a crab, hence the talk title. So as you can conclude from that, today we're going to talk about how you can use the Rust from Python and the other way around for profit and fun. All right, so first let me introduce myself. So I'm Bernát Gábor. I work as a senior software engineer at Bloomberg in a team called Artifact Repository Hosting. More importantly, I'm an open source contributor under the name Gábor Bernát on GitHub. And I'm also a member of the Python Packaging Authority by being a virtual env and build maintainer / author. More importantly, even, I'm also a husband to Lisa and parent to two small cub-sized Yorkshire Terriers called Silky and Junior. And I'm definitely going to use them to make this talk a bit more fun than otherwise would be. All right? So, I was born and raised in Transylvania. That's that wee green dot inside Europe. So you can blame my accent for that region. Nowadays, I'm living in Los Angeles. So, as you can see, I maintain quite a few packages, some more popular than others. The ones important for the today talk is going to be these last two, the PyProject.former and toxtoml.format. Why they are written in Rust, I'm going to tell you later, so you'll have to wait for that. So, what is Python? Well, this should be the easy one. If you don't know this, you're going to have some very surreal few days ahead of you. So, but don't worry, if you don't, we are a very welcoming community, so you will learn a lot. But Python is generally an easy to read and write clean programming language. It is garbage collected. What that means for you, you don't have to worry about memory. That's someone else's problem until you actually run out of it. Another main trait of the Python language is an interpreted language. What does this mean? It doesn't have a compilation phase. Rather than it kind of like you write some code and give it to some VM-like stuff, some virtual machine, and they're just going to make it happen and run. Okay? You don't have to have any compilation. And also, it's an optionally typed language, meaning you can add type annotations to the Python, but you don't have to. And if you do add it, the runtime will not use it. Your code not going to be run faster. Adding type information in Python is purely a kind of nice to have for yourself and your developer mates, rather than because the language wants it. Also, error handling inside the Python language is done via exceptions. So you need to do try except whenever something goes wrong. All right? And finally, it's kind of like a functional object-oriented language. What functional just kind of means that you can do streams and transformations. And object-oriented basically means you can write classes in the language. Okay? Most of the design paradigms and programming paradigms are kind of aimed around the one you're going to have in this language. All right, we went over the easy part. Let's go over to the hard part. I hope you're ready. So, what is Rust? Rust is a programming language created by Mozilla in 2010, technically, but released then in 2012, which emphasizes the following main design goals. It wants to be as fast as possible. How does this achieve this? It compiles to actual binary machine code, stuff that your CPU can read and run. It is also strongly typed. What does this mean? You actually have to care about types. If you want to create a method, you have to specify exactly, hey, this is my input arguments, this is the type for each argument, this is the return type for each of them. For example, here you can see creating a vector, you have to specify the size, you have to specify the return type, all that kind of fun. Another thing it kind of focuses on is making it easy to do concurrency. And when I say make it easy, I mean it makes it easy to not write bad concurrency, but doesn't mean that you're not going to be hard to actually write code in it. But it does through this custom ownership model, which is the ownership memory model. This is very different from the Python. The main way this manifests is that usually by default all the types are read-only. Why are they read-only? Well, because what is the biggest enemy for concurrency? Anyone? Sorry? Sorry? Yes, exactly. So why do you have race conditions? Because you try to read and write the same thing at the same time. If everything is read-only, you don't have race conditions. Problem solved, no? All right. So Let's do a bit of Rust, because if I'm going to tell you how we can use Rust from Python, you actually need to be able to read Rust at the basic level. So let's do some kind of like core principles. So Rust has this kind of like concept of panic. Why it is called panic? Because when this happens, both not just the application, you also gonna panic. In practice, what this means that whenever you throw a panic, that's basically something went wrong, I'm gonna quit, nothing can be done. You can actually invoke this kind of like crash the application error, so to say, by doing this panic exclamation mark call, and that's gonna trigger whenever your application runs this lovely stack trace for you to look at. Another core principle of the language is called macros. What are macros? Macros are basically kind of like a function, which you finish the function call, you finish an exclamation mark, and macros are a way to kind of like transform that code into something else. For example, if you want to print out a message to the standard output, you can use this like this print line thing here, and then the Rust compiler going to transform that to make it happen. How? It's an implementation detail. It just works. It's going to be whoever writes that macros problem to figure out how that happens. But you as a user just write that very short line, and then under the hood, the compiler figures out the rest together with the person that writes the macro. All right? Now, another core principle of Rust, it doesn't have exceptions. Because there are no exceptions, instead it has these two built-in types called option and result. As you can see, for example, here, if I have an option, which I can have it like be none by default, and I can make method calls saying, hey, is this empty? Or if it is not empty, give me the value of that so I can print it out. Or this is the result, where you can see like I can define, hey, this is the result type in which I'm going to put like a number, and then I can kind of like use the magical match statement to actually get the values out of it and do some path handling depending on each cases. This match might be kind of like something you already seen in Python, and that's the intent. That's the intent, because the Python match statement was heavily inspired from the Rust match statement. All right. So what's the difference between option and result? Because you can see both of them is kind of like there's something in it or there's nothing in it. Well, the difference is that generally you use option when the failure is expected. So for example, if you look inside the dictionary and you want to get a value out of it, it is very accepted or kind of like accepted that it might happen that the value is not in that dictionary. In that case, you're going to have an option. The result is more like something when that not happening is the failure. It's kind of like the exception case inside the Python programming language. All right? So another big trait of Rust, as I said, it's mostly a functional and trait-oriented programming language with very limited OOP, which is kind of like translates as object-oriented programming. What this means in practice is that you don't have classes. Instead, you can define kind of like structures. For example, here you can see I defined the data class structure that has the first and the second type, which is its type information. And then I can define on top of this type traits, which are kind of like an interface. And on this, I can say, hey, this is a trait that allows me to summarize the type. And then I can implement this trait for my data structure or data class. All right? Actually, let me switch here. Sorry. Yeah, I think that might be more readable. All right. So yeah, you can see here, basically, then what this means is that you don't have classes. Instead, you have to like kind of like do these shenanigans with interfaces, traits, and implementation on those traits. And that's how you kind of like make something similar to object-oriented language happen. Another big difference, as we said, because we love concurrency and we hate race conditions, everything is immutable by default. What that means that, for example, if you create this lovely vector and you try to add an element to it, the compiler will shout at you that, hey, this is not possible, don't do this, you're going to fail with an error. And the way to fix it is you have to specify this mute keyword in front of the type, and that can like define that, hey, this thing now can be mutated. And once that can be mutated, a whole different rule set applies on that type from the compiler's point of view. So then you might get some other compilation errors, but at least now you can mutate it. It also means that now it's very easy to cause against race conditions. So Rust doesn't solve the race conditions, it just makes it less relevant by default, because you have to explicitly state that, hey, this can be modified. Okay? Another big thing that you're going to see once you start reading Rust code is the return by default. If you write a method and in the last statement you don't specify a return, rather than you just leave there kind of like a statement, the value of that statement will be automatically returned at the end of it. Another kind of like hallmark of the Rust programming language is this one-stop package manager called Cargo. This is what essentially inspired a lot of similar implementations in Python. Initially, probably you're going to heard about PyO3. Nowadays, UV tries to be the same for Python, but Cargo was the first big programming language that went down this path. Let's have one tool that does everything, and the user doesn't have to worry about it. For example, here you can see I can use Cargo to build the entire program. I can use it to format my code. I can use it to lint my code, to run the test suite. All I need to do is Cargo. Okay? So now we did the quick Rust learning session. Let's go in then why we want to create this friendship between these two programming languages. Well, the obvious answer is speed, because, hey, as good as Python is and as easy it is to read and write, it's not the fastest thing on the world. And yes, we do have all these initiatives to make Python faster with Mark Shannon's Faster Python initiative. It's never going to be as fast as native machine code. All right? Another big benefit of Rust is reliability. And this comes from when I say reliability, I mean it is very deterministic and you don't get kind of like spikes, generally speaking, because of the programming language. And this comes from the element that Rust doesn't have a garbage collector. Rather, it uses its ownership model to create and release memory. So because of that reasons, for example, when someone, I'm blanking on its name, but someone tried to create a web server in Rust that you can add your Python application to it. One of the learnings of it is that once you use a Rust web server to run your Python code, you're going to have much less spikes, because there's not going to be much fewer kind of like spikes in your maximum response time, because the garbage collection never really gets triggered in that case, or it's a lot less. Okay? So another big thing is that once you try using, you can kind of like use to communicate with the Rust programming language. Now you have access to the entire ecosystem of the Rust programming language. For example, Python is very great and has a lot of things, but one of the things I don't think we really solved yet in the language ecosystem is writing a tone parser that actually can write out the changes rather than just read it. We have a reader inside the standard library, and that's great, but the one third-party package that you can use to write it, it's not as good to actually, if you want to like change the code. Why is that important? So for example, if you want to write a formatter for your PyProject.toml file, you're going to have run into this issue where you're going to run into weird bugs when if you try to update, for example, to translate the single quotes in the double quotes in your PyProject from a formatter automatically, you're going to run into issues where, for example, the comments are not placed correctly and all that kind of stuff. Luckily enough, in the Rust programming language, there's this great tool called Tableau. And this Tableau actually is something that has a very good TOML writer. And once you can make these two languages communicate with each other, you can actually write a TOML formatter by using the Rust implementation in Python. Yes, you're going to get some speed improvements, but let's be real. Formatting a TOML file doesn't really require that much CPU power, so you're not going to care that much about it. All right? So another big benefit is it's a slightly easier security model. Why it is a slightly easier security model? Well, because everything by default is mutable. If everything is mutable, it's very hard to cause race conditions. And another element of it is that you also never going to run into null pointer exceptions and stuff like that, which you can have in the C code, because the Rust ownership, the compiler itself takes care of that. Now, that doesn't mean you cannot write, you're not going to have security also in your Rust programming language. I mean, it's easier to have good one rather than impossible. If you have enough will, you're probably only going to take you maybe 5 minutes to create a security hole in your application. okay, even if you write it in Rust. So another big benefit is that concurrency. Rust doesn't have a GIL. Well, Python not going to have soon either, but until that day comes, hopefully, because it's not sure yet, then until then you can use Rust to use all your CPU cores for your CPU intensive tasks rather than be limited by the Python programming language's limitations. All right? So, and finally, Rust is considered one of the most challenging and rewarding programming languages. So why write only Python when you can have experienced the joy and misery of also using Rust? At least you're going to feel accomplished and challenged. All right? So the way these two things are going to work today, it's actually using this project called PyO3. This is the mediator. You can think of it as a translator that makes this snake and this crab actually be able to talk with each other. This is the project that allows you to run Rust in Python, but also allows you to run Python in Rust. Why do you want to run Python in Rust? Well, because maybe you write a code and you actually have a bit of business logic that's only implemented in Python, and you don't want to duplicate that code in your Python and Rust code. Then you are able in your Rust code to say, hey, call this method from the Python ecosystem, and that allows you to kind of like cross this cross-language barrier multiple times and reuse as much code as possible, because maybe that functionality is not really performance critical, so it's easier just to be able to do the other direction too. But I will say 95% of the time people use PyO3 to run Rust code inside the Python interpreter. All right? So if PyO3 is the project that makes the translation happen, Maturin is the one that actually does the heavy lifting and actually interacts with it. This is what you're going to be communicating with it. What is Maturin? Maturin is a PEP517 backend. What does this mean? Well, this is kind of like a packaging concept, but generally speaking, when we're talking about packaging in Python, we talk about some kind of front end and back end. The front end is stuff that you communicate for it. For example, pip that you use to install a project is a front end, because when you type in your terminal, you're going to type in pip. As opposed to that, the back end is the stuff that actually creates artifacts that you can install. So for example, whenever you type to a folder and you see it typing like pip wheel, and that builds a wheel, you communicate with the pip, but actually what's going to spit out that wheel file is going to be the backend that you're using. Now, Maturin is the backend that is written by the PyO3 that actually allows you to communicate with it, and it's going to spit out that wheel file to actually work with. But under the hood, it's PyO3 that makes the translation between the languages. You can think of it, Maturin, as kind of like the stuff that gives you a blob that you can use and install in your other machines. Okay? There are alternatives to it. For example, setup tools, Rust or Rust NumPy, but these are generally less used. Most of the people just use Maturin for this. So, how popular is Rust with Python? I enumerated here a few, I would say, mildly popular packages that we use nowadays. You can see cryptography has around 350 million downloads a month, or Pydantic, or JSON, or RUF, tokenizers, UV. These are Polars, Deltalic. These are all projects that are using PyO3 and Maturin mostly to give you very performant logic inside your Python application. And I assume most of us, even if not directly, indirectly, been using these tools for the last few years. And here is, for example, kind of like a popularity chart. You can see its use and popularity is only increasing. Given that you can see here, roughly speaking, every month there are around a few hundred million downloads, we can say that it's pretty much production ready. Okay? Now let me put this notification off. So let's go into a use case. So if you want to learn about how we do it, we need to have a kind of like a problem we want to solve. The problem we want to solve is find the first n prime numbers. What is a prime number? Well, a prime number is a number that is greater than 1, and it's not the product of two smaller natural numbers. You can see here, for example, how such a method's interface would look like. You can see that we have kind of like an argument how many prime numbers we want, and it's going to return a list of those numbers. So, for example, the first 5 prime number would be like 2, 3, 5, 7, 11, because no number divides that other than the 1. So it is kind of like a naive pure Python implementation of that. Okay? So, how does this actually work? As you can see, we have a list that we're going to return at the end, and we're going to populate the prime numbers into this list. Then we have kind of like a for loop or while loop that we keep going with the numbers starting from 2 until we find enough numbers to reach our goal. And inside the loop, we basically go over all the previously found prime numbers, because if we already found every smaller prime numbers, anything that divides it must be divided by one of the smaller prime numbers. So we just take a for loop, and if any of the previously found numbers divided, then it is not a prime number. And if not, then we can use this else statement for the for loop, where we can kind of just add it to our found list and keep continuing. All right? So fairly simple. How does the Rust implementation of this look? This is the Python version of it, and then this is the Rust version of it. Now, as you can see, it's just a bit more complicated. And to go over it a bit, you can see the first big difference is that we have to have the way you define a method is slightly different, and we have to specify the type annotations, but we already did that for the Python implementation too. Then we have a same way we define kind of like a list, which in the Rust world is called a vector. And in this vector, we're going to keep adding elements until we have enough number. And we also have this kind of like index that we again start with 2. As you can see here, we have this mute keyword because this is actually a variable that's going to be increased through every for loop. So we need to mark it mutable. And then we have kind of like this for loop where we just go over all the previous numbers and check if it divides. Now there's a bit of complication here that comes from that Rust doesn't have an else inside the for loop. So instead we have to use a variable to actually make that happen. And this is what this divided flag does. This is just a flag that we check, hey, did any of the numbers before divided it? And if it didn't, then at the end we're going to put it inside the list. So this is just a side effect that Rust doesn't have an else on your for loops. But otherwise, if I go back a bit, you'll see that it's just slightly more complicated. There are a few extra lines, but if you spend a few days playing around with it, you should be able to transfer most of your simple Python code into simple Rust code fairly easily. All right? So now that we're done with that, let's see how we actually make this happen. Let's jump into this. So in order to expose some Rust code that we return to Python, we're going to be using this PyO3 project. And the PyO3 project uses procedural macros to actually make this happen. What is a procedural macro? Well, I told you earlier that a macro is just something, was like a method that you can put an exclamation mark on the end of it, which then the compiler is going to transform that line of code into something else to make it happen. Procedural macros is those on steroids. Now, rather than just transforming that one line, the compiler will transform the entire method. So here you can see these are the procedural macros. They are used by this comment, kind of like hashtag square brackets. And in this case, when the Rust compiler sees, it knows that, hey, these are my procedural macros, and then it's going to transform this entire body of these methods. More or less, you can think of it that way. So in Python, we put code inside modules. And inside modules, we can have either data or variables, but we're going to have some information in it. This is very much a thing when you're going to expose some Rust code inside the Python language. You need to specify, I want this method inside this module. And that's what you see here. We first define that, hey, we're going to have this first end method, which is a function. So we're going to just mark it that this is a function that is exposed inside the Python layer. And then we have the second segment, which is basically saying that I'm going to define a module called this underscore lib. And inside this module, I'm going to add this function, which I defined earlier. This is just telling basically to the PyO3 mediator that, hey, this method will live inside this module, and it is a function. And once you add these kind of like semi-annotations, at least you can think of them, but they are called procedural macros, the rest is going to be taken care of by PyO3. You don't have to worry about it. So once you write that kind of like small annotations on the top of your what you call Rust code, you obviously need to actually add some metadata inside the cargo.toml file. This cargo.toml file is basically the same thing as PyProject.toml file for the Python language. This TOML file will contain some metadata about the project itself that you can see here at the top. But more importantly, we're going to have this bottom section where we're going to specify that this Rust program depends on the PyO3 and its version. It also has a lib section where we define what is the name of the method, which Rust file this method lives in. But ultimately, with these 5 lines of metadata inside your cargo.toml, the rest should just work. Now we have here also some features enabled. Features are kind of like an extra feature of the Rust programming language. Those are basically features that you can optionally enable. It's kind of like when in Python, you can have like extras installed for a package, and you can say, I want this additional functionality that doesn't come out of the default. This final 2-3 lines, these features, it basically enables that. Why do we need those 3 lines? I'm not going to tell you today. It's a bit complicated, but you can just add it and it works, okay? You can read the PyO3 documentation for more advanced explanation of that, okay? Now, once you define that cargo file, you also need to define your Python project. Why? Because, well, this is going to be a Python project at the end of the day. So you need to tell to the Python tooling what to use and how to use it. So this is where you can see that we specify that the build system for this application is going to be Maturin, and it requires this Maturin version. More importantly, we also specify that we're going to the binding is going to be handled by PyO3, and the manifest is inside this cargo.toml files. We also specified what Python package this will generate and what is the module where the Rust code going to live in. So for example, here we're going to see that we put this Rust binary blob inside primes_lib location. And once I have that, inside my Python file, I can just do this, where I see from primes_lib import first n. Why does this work? Because here above in line 11, we actually specify that we're going to put the Rust binary inside this module. So then I can just import it, and the rest works. Okay? So I really don't want to join this event. Thank you. So how is the final layout of a project works? It's going to be mostly something like this. What you're going to see it here is you have some Rust section. The Rust section basically has the cargo.toml file and the log file attached to it and some Rust code in it. And then you're going to have a Python section where you have a module, and you also have some PyProject.toml file. And here in case I also added the test in Python, because testing is always a nice thing to do. All right? So was it worth it doing all this effort? Well, as you can see here, if I benchmark my implementation of the Python and the Rust, you can see that I experienced a performance increase of 10-fold or 12-fold, to be more precise. Does a 12-fold performance increase worth adding 5 files? Depends on your use case, maybe. If you actually make money by being as fast as possible, definitely. Okay? So now let's go a bit deeper. How does this actually work? What happens when you do some installation in it? In order to speak about this, we need to briefly talk about the import system. So question, how does the Python interpreter knows if something is importable? No. No. Any other opinion? Like if you type in import functions, how does Python know that this exists, or what to do or when to do? Yes and no. I see where you're getting it. And I think the short answer is it doesn't. It has no idea if something is importable or not. Instead, it goes, hey, I'm going to try to see if I can do it. If not, I'm going to throw an exception. All right? So this follows the Python mantra. It's better to ask for forgiveness than permission. So when you type in something, at that point in time, it has no idea if that's going to work. Instead, going to try. How it's going to try? And that was most of the people were getting at. It's going to use a few kind of like configuration knobs to try a few things and see if any of them succeed. All right? So the importers that is able to exhaust, but you can extend it and add your own importer, it's going to be defined in this sys.metapath location. Here, for example, you can see that out of the box, if you do nothing, CPython going to give you a built-in importer, a frozen importer, and a path finder. What are these things? Or importantly, the built-in importer are stuff such as, example, like your operating system module. That's what comes. Basically, it's a module that is built into the Python interpreter itself. You're not going to find the os.py on the file system. Now, the frozen importer is something that you're going to find it on the file system, but it's still a binary blob that you're not going to be able to modify. But more importantly, 99% of the time, you're going to use this pathfinder thing. And this pathfinder thing, which finds modules from the path, the file system, is something that you're actually going to be using this sys.path configuration on its own to look for locations where to import stuff, to find stuff. Now, this importer, it's not only able to import Python files, but it's also able to import binary files. Binary files such as SO or DLL files. SO is on the Unix machines, DLL is on your Windows machines. Now, obviously, in order for a binary blob to be importable in Python, it needs to satisfy some metadata and need to look a certain way. But if it looks a certain way, it is importable. Yeah? So, ultimately, if you actually check your site packages folder, once you build the Rust code, it's going to look something like this. You can see that inside the site packages, we have some what I call the project itself. It has some Python code, but more importantly, you see it has this underscore lead abi3.so. This is the binary blob that Maturin going to spit out for you that is compatible with the Python import system. So when you try to import from primes underscore lib, the Python interpreter will look out on the file system, and once it bumps into this, hey, this actually satisfies the primes underscore lib name. It is importable, it has that metadata, so I'm going to be able to actually load that code into the interpreter. All right? So ultimately, what PyO3 does, well, what Maturin does is whenever you build your Python project, it's going to take your Rust code and transform it into this SO file. Okay? And this is why it was important whenever we defined it, what is the name of the SO file, both in the Rust code and the Python code, because this is what tells them Maturin where to put that lib.so, and this is what then governs how you want to be able to import it or discover it on the file system. All right? Now there's some additional metadata there on that site packages folder, but it's not that important for this talk itself. So what does PyO3 offers? Because as I said beforehand, Maturin is the one that actually creates that SO file for you. What is PyO3? So PyO3 is the layer that handles the communication between the Python and the Rust code. What this means, it's going to handle the Rust panic for you. For example, I told you before that Rust had this concept of panic. And what did I say? When the panic happens, the program needs to shut down. Because of that, obviously, generally speaking, when something bad happens in Python, we throw an exception. So following that reasoning, it does translate a panic inside the Rust code into an exception on the Python world. But because you shouldn't catch this exception, because it's undefined what happens once a panic happens, because once a panic happens, the Rust interpreter, quote-unquote interpreter, wants to shut down the entire application. For that reason, this panic going to be translated into a base exception. Why a base exception? Because most people catch exceptions, not base exceptions. You can catch the base exceptions, but there's no guarantee that's what's going to happen. So it's not recommended. But any panic that happens in your Rust code going to be translated into base exceptions. This is the translation layer that the PyO3 will do for you. Another thing it's going to do, it's going to handle the reference quanting between boundaries. Now we're passing data between the Python interpreter and the Rust interpreter. The Python interpreter always uses reference counted garbage collection. So someone needs to do the bookkeeping to make sure that your Rust binary or data doesn't get evicted halfway through running the application. This is what the PyO3 again will do for you. And it will also do the argument parsing back and forth. All right? And finally, it will actually call the Rust user code. So if you type in from prime _ lib first n, this is the one that's going to be able to go into that generated SO file or DLL file and look, hey, this is how I'm going to pass information from one barrier to another barrier. All right. Now you feel ready to take over the world, write some Rust code. Let me ruin a bit your worldview. So once you start down this path, there are a few complications and things you will have to consider. The first thing you need to do is you need to deal with type conversions. Yes, in Python, if you want a number, you just type a number. And is it small, big, doesn't matter. The Python interpreter will handle it for you. If that number can be 10 billion or just 5, the same way you do it, not in Rust. In Rust, for example, just for the integer, you can see we have this lovely 16 variations. So you actually have to think out of these 16 numbers, which one I want for my application. Another thing you have to consider that even though it is small, there is an overhead to cross between languages. As I said beforehand, PyO3 will do for you the transformation of the binary data and passing back and forth the data between the languages. There's still work to be done. So if you're going to do a lot of this kind of like crosses between the languages, your return on investment going to decrease. So don't necessarily do a lot of it. Try to have a few between the two code. It is mostly useful accordingly for CPU-bound calculations. If your application does a lot of system calls or network I/O, for example, web servers is one of these examples, you might not get the most benefit out of it because most of the time maybe your Python application is waiting for the network socket to respond with something. Being a more performant wait engine doesn't help you there. You're still waiting at the end of the day. Okay? Now another kind of like complication is Rust is not supported on all platforms. Rust uses essentially the Clang compiler. So anywhere the Clang compiler will work, Rust will work. Anywhere the Clang compiler will not work, your Rust code will not work. Even though your Python code might work, the Rust will say, no, thank you. Things to consider, mostly like more older versions of Debian, for example, more file onto it, or some FreeBSD also might have trouble with it, or any new applications. So for example, I don't know, if your company just creates a new platform, a new architecture, most probably it will not work there, okay? Because the Clang compiler doesn't know how to generate binary code for that. Now, another thing you need to consider is that Python is great because you can publish just one package and any Python interpreter on any platform and machine will understand it. Once you start spitting out binary blobs, that's no longer the case. If you don't want your users to need to have a Rust interpreter, a Rust compiler on the machine, you will need to make sure that you generate binary blob for every architecture out there. And when I say every architecture, I mean most of the one that is being used. And this can be quite a few. So for example, you can see here for the PyProject.format project, if you look on the published wheels for it, you see that I have a source distribution, which is the easy one. That's just the raw code. But if I actually want wheel, because I don't want my user to have Rust installed on their programs, I need to generate a wheel for every platform. So for example, here you can see the first one. It's a many Linux wheel only for PyPy 3.10. And yeah, for the x86 architecture. So now we're talking about CPU architecture, Python interpreter version, and Python interpreter flavor. So if you multiply all of this, you're going to end up with 20 plus wheels that you need to generate in order to make your users happy. And they don't have to have the Rust installed on their application or on their machine. Luckily, if you're using GitHub, Maturin has this built-in generate CI subcommand, which allows you to generate a GitHub workflow that takes care of all of this, and then you can use the GitHub infrastructure to generate all of these wheels and publish all of these wheels. For example, here you can see, once you generate it, as of today, it's going to generate you 22 packages for every version. So now whenever you publish a package for your project, you're not going to end up with one package, but rather 22 packages to publish. But if you're using GitHub Actions, it is fairly easy, and you're going to end up with kind of like a release pipeline like this. As you can see here, it has 8 jobs just for the Linux operating system, 2 for macOS, and then 2 for Windows. Now this matrix and 8 jobs. These are mostly for architecture dependent. Now, actually, each of these jobs will generate multiple wheels under the hood for each of the interpreters. So you're going to have kind of like a big list like here. But at the end of the day, this just works. So you don't have to worry too much about it. Obviously, if you're going to try to use Rust within your own company, where you can't use GitHub Actions, it's going to be a bit more complicated because you need to have availability to all the, inside your CI, to all the platforms that you want to target for your users. So for example, if your users are going to use macOS, you will need to have a macOS machine in your CI within your company to be able to actually publish wheels for that platform. Because without it, if you only publish for the Linux one, whenever someone's trying to install your project on macOS, it's going to fall back to the source distribution, and then Maturin going to throw a lovely error at you. Hey, in order to create a wheel to install this package, I need an actual Rust compiler on the machine. So now the user will need to install that, and it's more headache at that point. Okay? So I heard you. We talked about Rust, but we had this thing called Cython for years. Why don't we just use Cython? Why do we try to do Rust? Beside this element which I said earlier, that why don't we experience the joy and misery of writing Rust code? Well, nothing stops you from it. So for example, if you see this Rust code, this is how it would look in Cython. Now, it is arguable or debatable which one is better or worse, but at the end of the day, you can use Cython the same way you can use Rust, and most of the time, you're going to get very similar performance. So for example, here you can see I benchmarked the Cython implementation and the Rust implementation, and they're basically within variants. It's basically no performance difference between the two. So if you want to use Cython, you can still use Cython. Cython is just as good. Maybe it's not as, doesn't have such a rich ecosystem as Rust has, but then you don't have to have a Rust compiler. So pick your poison kind of situation. All right. So let me use the next minute to actually vent my frustration with Rust. So as someone who wrote a lot of Python code in the last 15 years, when I start writing Rust, this is where my, I would say, complaints about the language. Well, the first thing is you actually need to deal with making the compiler happy. This is what most of the people refer to as fighting the borrow checker. What this means is because of the ownership memory module, if you actually take a reference to any kind of like object in Rust, you own that reference. So if you're going to try to access it from another method, that reference, the Rust compiler is going to throw an exception that, hey, only one person can own this object at a time. Why you try to access from 2 locations? This becomes especially complicated once you start needing to situations like, for example, graphs or linked lists. Anything like that, where you kind of like have a lot of references that you pass around between different methods, it's going to be a nightmare to deal with in Rust because you have to like kind of like tell to the compiler at every line that, hey, I'm fine to doing this, make it happen. You have to do like more advanced concepts like boxing and stuff like that to actually make that happen. Now, another kind of like big problem or gripe I have with Rust is that the debugger is not as powerful as Python. Generally speaking, if you want to debug a Rust code, you can go as deep as print out the value of a variable. Not to mention, if you actually put the debugger put a breakpoint somewhere in your code, what you're going to see is basically, because it's machine code, you're going to see a lot of pointers, and then you have like translate the pointers to actually see what is the data inside it. But more frustratingly, you can't actually do any complicated method calls or anything like that, do an expression where call this method to other expression. No, it's basically very bare bone. If you want the data, you can look at the data through jumping to some pointers, but don't really call any method calls, stuff like that. Why is this frustrating? Well, because I don't know about you, it's definitely a skill issue, but I tend to write more bugs than I care to admit. And then I have to actually find them. And I tend, in my experience, to use the debugger quite often to do that. And if the debugger is not as powerful, it makes me less efficient to actually find the issue. And I know people praise Rust for having great packaging, but I think, and Python is known as this horrible packaging experience, but I tend to think that I set up packaging once and then it works. It is painful the first time I set it up, definitely, but it's a one-time pain. As opposed to that, debugging, I write bugs every day, or at least every other day. So it's more often going to deal with the bad debugger than with the great packaging. All right? So generally when I speak to Rust programmers, hey, so what do you do? They were like, I just put some print lines in there and restart the application. Now this is where it comes to the other problem, because it's a language that doesn't have binary blobs published. Everything is compiled from the source. Whenever you add a print statement, you have to recompile everything. You have to restart your application. You have to reseed everything to it. It just makes the entire loop quite a long process to like, okay, let me try to replicate what the issue is. All right, so we'll have to deal with that. And yeah, the compiler can be slow. Rust doesn't publish any wheels. This is a great way to not have problems. One of the big problems that why the Python packaging is so difficult is that we try to publish binary blobs into a central location, and we expect that binary blob to be compatible with all the platforms that the user is going to run. This is great because the user doesn't have to set up any dependencies on the machine. Everything kind of like just installs in one go. And most of the time it works, but when it doesn't, yes, you're frustrated. But opposed to that, Rust doesn't publish any binaries. The only thing, if you look in this package registry, is going to be the source code for everything, which is great for not having to deal with that problem space. But then it means that whenever you set up your applications and you do the first time build, it's going to take 5 minutes because it needs to rebuild the entire world from scratch every time. So this causes quite a long compiler sessions, especially as most of the time the compilation for a given project is sequential. So if you have two dependencies, they're going to be done one after another rather than in parallel. So generally speaking, the compiler can be, and yes, once you compile it, there is some cache. You can reuse it. But even if you do a print line addition, it's going to be now a new compilation that you have to redo the binary blob and rerun it, right? And another thing that I occasionally run into is that you find all these great packages where the user solves 70% of the platforms you want to target, but you also care about the 30%. So you might not be able to run a given package because it doesn't work on some of the platforms that you actually care about it. Okay? So yes, and yeah, I think that went more than 1 minute frustration. Okay. But generally speaking, once you go past this, and okay, you look past it and you deal with it, using Rust from Python can be quite good. Yeah, like it's generally a good one. It's not going to be a smooth ride, and you might run into the bumpy learning curve. But expect that whenever you learn a new programming language, struggling is normal. Every one of us struggle. You're going to start here where you're like, hey, I saw this great talk at PyCon. I'm going to write some Rust code. You go up, and then you're like, damn, this is hard. Why do I get these compiler failures, all these things? But then if you keep at it and you read a few more documentation, you're like, oh, I know everything now. Before you go, I know nothing, because now I've run into this complicated problem. But keep at this curve long enough, you're going to end up in those bottom or top right corner, also called the Rust Nirvana, where you're going to be very proficient. It is also much easier nowadays because we have these new overlords called large language models. So you can just give your Python code to a language module and say, hey, write Rust for it. It's going to spit out mostly good things. Will it have a few bugs? Yes. But it will mostly work. And then you'll only have to deal with those few bugs at the end of the day. All right? So I posted a few reference pages for you here. That's stuff that you can read to learn more about it. When it comes to an IDE, I find that the Rust rover by JetBrains is probably the most easy to use. You can also use VS Code Rust. It's not as good as Rust rover, but on the other hand, Rust rover actually has a paid license if you're going to make money of it. So there's something for something. But I'm going to finish on this one. This is a kind of like a advice my first boss gave me when I first joined the first company, that there is no such thing as a stupid question, just a missed opportunity to learn more. When you're going to go through this conference throughout the next few days, I want to approach this everything. Is it fine for you to not understand things? Definitely. The way we learn is we look at things, we try to understand it and ask questions about it. None of us knew everything from day one, because the way most of us got good at our job was by asking a lot of dumb questions until we kind of like didn't have any more left. And with that, I'm giving you the platform to ask your questions. Thank you.
Hi. No, thanks. This was a super informative talk. Like about a year ago, I actually tried to write a Python wrapper over a Rust library, but then things which I was wondering is, are there like good examples of that, like in terms of some open source projects which are like you would say are good for like kind of learning from, or like as a template of doing that in a like best practice way? Like I tried also looking at polars, but I mean that's obviously a much more like complicated one. I don't know, maybe I'll look at PyProject format or something like that.
Yes, I mean, as you can see, a lot of I'm not going to go all the way back to the board, but a lot of the popular projects are quite complicated projects. So I found that the PyO3 documentation is quite good for general simple questions or like concepts. But if you want to like play around, I do find actually like the PyProject format, it's a fairly simple, but because the actual code is maybe, I don't know, we're talking about under 1,000 lines, and it has tests and everything. So it's quite easy to grab with, and plus it's easy to get kind of like quick feedback of it. Because I don't know, for example, if you're going to do something like pydantic, if you change something on that side, it's not that easy to see the interaction. But for example, in a formatter, if you change some Rust code, you can see how the TOML file gets changed differently. So for that, yeah, maybe PyProject Format is a decent project that you can look at and see the simple-ish example. Now, the one thing I will caveat that with it, because I also maintain the Tox project, and the Tox project added TOML support lately. So I also write a TOML formatter for the Tox project. And because I hate maintaining the same code in 2 locations, I put them in a single GitHub project, which then causes a bit of complications. So, but I think if you go back, especially in the repository, and you check out the state before I did that extension, maybe like 6 months ago, that's going to be a fairly simple single contained project example.
So I'm going to be that guy and give you a comment. Your comment about Cython, I've personally shipped buggy Cython code that does undefined behavior, and that happened on real user systems and caused them to generate garbage. So, like, Cython doesn't have the safety rails that Rust has, and if you write buggy Cython code that generates C code that has undefined behavior in it, it doesn't really do anything to protect you from that.
Yeah, I definitely agree with that. I will say that, just what I said earlier, that it's definitely possible to write bad code in Rust too. So it doesn't solve you, but it does have more guardrails against it.
So I do have an actual dumb question. You're going to groan at this. So as everyone here knows, Python is like a beautiful language, right? And Rust is incredibly ugly. Do you have any recommendations as far as general guidelines to make Rust more readable? Especially when trying to integrate it with Python?
I will say that Rust is ugly, especially if you hate curly braces. This is something I didn't address at the beginning. Python uses indentation to format your code. Rust uses curly braces. So if you love curly braces, you're going to love Rust too. If you hate curly braces, you're going to hate Rust too. But I will say, to make easier, I want to say that both Clippy and the cargo formatter, both are quite very good. Like, even if you write code that works, the Clippy, the linter, similar as UV, going to give you very good advice. You should do this instead, which is going to be easier to read and nicer to operate. So if you use, and then the cargo formatter, it's also fairly good. It's going to make your code look as nice as it can be. So for example, one of the things I don't necessarily covered earlier, if you look at the code, Rust, similar to Python, you can put curly braces, not curly braces, but like braces around your if statements, but you don't have to. So for example, the formatter will remove those for you to make it look cleaner. So just use the formatter and use Clippy. It does, I will say that there is a built-in linter in the cargo itself, because Clippy is a third-party package, which is not as powerful. So I would definitely recommend, if you start writing Rust code, especially as a beginner, do set up the Clippy, which is the third-party, more advanced version of the linter. And that's going to give you quite good advices on how to modify your code. Sorry, there's a question here.
Thank you for your amazing talk. I have a question regarding the wheel files. So I saw that you are building around 20 will file depending on the platform and the architecture. Why don't we generate just any will file, the one will file which works for any platform, any architecture? Because I have seen in many Python packages that they just have one will file.
Yes, and comes down to the Python C API. Now, the Python C API is a great thing, but it's an ever-evolving thing. There has been efforts to kind of like make it define a core C API, and there's an advanced C API. What's the difference between? There is this ABI 3.8 that they call it. That's basically a subset of the C API that is guaranteed to work on any Python interpreter 3.8 or later. So in this case, if you're going to build a wheel, you only need to build one wheel per like Linux, Windows, because all Python interpreters will do it. The downside of doing that is though that now you're not able to use the more advanced functionalities of those Python C API because you're only using a core segment of it. And it's also something that needs to work the same way on 3.8 and 3.14. So there's and because you do that, potentially you're not going to be able to use most of the, let's say, new improvements and performance increase on the later C APIs. So that's for that reason, Maturin out of the box tries to generate a wheel for every Python interpreter version, because that way it can generate you the most performant code. But it's definitely possible, but you still need to generate a wheel for every architecture because, for example, x64 and an ARM processor has a totally different architecture. You need a totally different binary blob for the processor to be able to understand it. You just decrease the number of wheels you need to generate at the cost of some potential performance. And again, depends if you care about it or not.
Yeah, thank you for the talk. I wanted to ask a bit more about the GIL interaction. So is it so that the GIL is released once the Rust function is called, once the arguments are converted? And if so, once the Rust code runs, you can't touch any Python objects directly?
You can, but you need to use the PyO3 interface. So I didn't cover that example, but I mentioned at the beginning that you can call Python from Rust. So PyO3 does have, which PyO3 here is some Rust import package. It does have an interface to talk with Python. So that way, but then the PyO3 manages that. So once, for example, your Rust code calls into the Python, then the PyO3 will hold the GIL inside the Python ecosystem.
Yeah, that makes sense. Thank you.
Welcome. There's one more question ahead here. Front.
Hi, thank you very much for your talk. So one of the points of you encouraging to use Rust in the beginning was, if I remember correctly, one thing is having a more stable performance, because if you write Rust, you don't have this problem of like managing memories and stuff. And also the second point being less bottlenecked by the GIL, but is it only for Rust or is it general for extension modules?
I want to say I would say depending on your programming language. I mean, C and Rust both have the same concepts, but if you write something in C or Rust, neither has a garbage collection. Ultimately, what potentially causes the spikes in you for the response times might be whenever the garbage collection decides that I'm going to look at the world, I'm going to clean up the garbage. So basically that operation, when that happens, the entire Python C interpreter is put on hold, like a pause button. Until that finishes, nothing has been done. So that might cause like a few milliseconds of spike in your response times because now nothing's happening. Now, any language that you use that doesn't have this, the same for C or Rust, will not have to deal with that problem. So it works both ways.
Thank you. I have one more question. I had to maintain, I didn't write from scratch, but I had to maintain an extension module. And how difficult is it to debug, when you have like have to write Rust compared to C plus or C or C++ with Python modules?
Marginally comes down, depends on your luck, I want to say. So it depends on what features you're using. C and C++ has been around for 40 years or whatever. So obviously the tools are a bit more advanced. They're a bit more. Now the Clang one is decent, but for example, even from it's similar, you can have even in C++, where for example, if you're using templates, the same applies that the compiler, when you use it, knows if it needs to generate that code for or not. Rust does the same thing. So for example, if you use some that is potentially kind of like a generic inside Rust 2, the compiler, the GCC, might not actually have the code to understand that, because maybe you didn't use your code, even if you used it only for your debugging session. If you had the debugging session that's not already loaded into the memory, it cannot actually translate it. I found what generally works the best is you're going to have your own test suite on the Rust side that basically just tests at the Rust boundary level what happens, and that's how you debug bugs inside the Rust code rather than do it from the Python. And then on the Python side, what you only put in your test is basically making sure that the way you expose it in Python still works. And then you're basically just writing Rust code, both from testing, debugging, all the way until you need to cross that boundary from your Python code.
Thank you.
Welcome.
I'm really curious about how you handle sort of the type marshaling between Python and Rust code. I know you talked about like, declaring a number in Python is like really easy. Do you have any like practical advice for how to manage the connection and bridges between marshaling that types of like data types, basically?
I will say that, as I said before, and yes, you have to, you need to think about what type goes to what type. But once you make that decision and you define your, for example, if you want to expose a data class and that's going to transform to a data class in Python and data class in Rust, those where you have to define the types on both of the sides. Well, technically you don't have to be on the Python side, but you might have a type annotation just so that the Python in world users know what kind of type you expect. But once you define it on the Rust side, what is the type? It is fairly, like PyO3 is very good at making the transformation happen. And I used like setting or option classes, and I used files and numbers and strings. And with those, I didn't have any more issues. Now, I didn't try to do something like Pydantic does, where I need to like marshal more complicated advanced classes. So I don't really have the experience on that side. But I will say, as long as you only care about transferring data structures and simple types, or built-in types, those most of the time you don't even have to think about it. PyO3 will just take care of it. The part you have to think about it is that, for example, if it's an integer in Python, what is the actual underlying architecture type on the Rust side? But that comes naturally when you kind of like define your Rust code on interface.
When I've been working on some project, most of the time I need to debug the source code of the Python third-party library. And for example, if I use a library which is written in Rust, is it possible to during the debug to step in and check the source code? I assume it's not, but
I want to say no and yes. It is not possible to debug it that way. However, because obviously if you have a Python interpreter, you're not going to have the Rust interpreter. However, there are tools that can help with that. For example, there is this tool that got open sourced by my company, Bloomberg, called PyStack, which allows you to also see the C-level stack trace. So if you attach that, technically you can see at least the stack trace. And I say it because Rust, everything is published as a source. You always have access to the source code itself. So if you have a smart enough ID, that can make the translation. And you can see, but you're not going to necessarily be able to like see the structures and the data types inside the Rust code when you're running inside the Python.
Thank you.
Thanks for the talk. I'll try to be brief. I mean, one of the good and bad things, of course, of the Python ecosystem is that there's a lot of users and there's a lot of feedback out there on internet, right, in terms of posts or how to solve problems and things like that. However, I don't know about Rust, and I would like to know, like, what's your feeling about like the community support and like how, like, when dealing with problems, how hard is it to see if there's a solution out there already and try to benefit from it?
I want to say most of the, obviously Rust has been around a lot less than Python. So generally there are a lot fewer Rust users than Python. But the people generally who do write Rust are all generally nice and helpful. There are also some language features. For example, you might run into a bug. For example, one and I run one of the bugs where the entire application just panicked because there was a bug in a dependency. And then I created the pull request. But one of the good things about Rust is that you can actually install not just publish packages, you can actually install straight from the GitHub. So if someone releases a fix, you can just patch your, even if they don't release or don't accept it, it's fairly easy to fork the project, fix your issue, and then in your packaging you can specify, don't pull this from the crates.io, which is the PyPI version of it, rather than pull it from this fork I have, and the Rust compiler going to install it and everything going to work. So from that point of view, even though the ecosystem is not as rich and maybe not as many users, it is fairly easy to work around issues you might run into, assuming you're comfortable enough debugging other people's code and fixing it.
Thanks.
All right, if no other questions, thank you very much for coming today and enjoy the conference.